Turner is the Chief Operating Officer for Controlled Thermal Resources, and their website is C-Thermal. So just the letter C and then the word thermal .com, and you can go to the website and there's a lot of information there. And Jim is leading the company's project at the Salton Sea. Controlled Thermal Resources was established in 2013, and it has headquarters in the Imperial Valley, California, and also in Brisbane, Australia. Jim has a BA degree in physics from Texas A&M and more than 30 years in senior management roles in renewable energy, primarily geothermal, including business development, engineering, and operations. He has served as vice president and general manager at Cal Energy, now Berkshire Hathaway Energy, with primary responsibility for their Salton Sea geothermal operation. He has been senior vice president of operations at Altarock Energy, focusing on engineered geothermal systems, and senior vice president of business development at Energy Source. Jim has led a specialized drilling team as well as a chemical formulations company, both as president. Jim's early career was with Dow Chemical, where he specialized in engineering and technology management. So with that, Jim, I think I'm going to share my screen here. This will take a second. And then you can start with your presentation as soon as you see it. Okay, there we go. You should be ready to go.
Yeah, there it is. Well, thank you, Mike, for the opportunity. I'm glad to be here, and good evening to everybody. I wish I could see you, but I can't. But please don't hesitate to ask questions, and I'll try to tell you a little bit about what we do out here and a little bit about the history at the Salton Sea and underground underneath the Salton Sea for making power and extracting lithium for batteries. So maybe we can go to the next slide there, Mike. So a little bit of history. That's actually a picture of the Salton Sink before it filled up with water this last time. And as you can see, that's the new Liverpool Salt Works. It covered about 1,000 acres out there back in the late 1800s. And we'll go further into this in just a minute, but what you see is a lot of salt out there. If you were to dig down into the ground, you would find essentially layers and layers and layers of salt, probably all the way down to maybe 10,000 feet or so. And that's a result of over millions of years, the Salton area out here, which used to be a big, deep crevasse, would fill up with ocean water, fill up with Colorado River water, dry up, it would come back, fill it up again, and pretty soon we have what we have here today. And so there's an immense amount of salt underneath. There's a lot of water underneath that's trapped in that valley. And what it did is it created the geothermal brine resource that we have today. This brine resource has no connection to the surface. It actually starts at about 4,000 feet down, almost a mile down. And for all practical purposes, it extends to maybe 2 miles or just a little bit further. And that's the resource that we tap into for producing renewable energy, and pretty soon to extract lithium from that same salt water that's down in the ground. Next slide, Mike. Just to give you a little bit of an orientation here, this picture, you can see the dotted line near the bottom, just above the word Mexicali. Mexicali is the large city on the Mexico side of that line. That's the U.S.-Mexican border, that dashed line. Mexicali has, I think, almost 2 million people today. And if you go north from that, you'll see the town of El Centro. The next town that's not shown is Imperial. That's where I'm sitting right now. And then the next town up is Brawley. And then as you go further up, from the Mexican border to the southern end of the Salton Sea is probably about maybe 40 miles. there's two rivers that empty into the sea. Both of them are very small, the Alamo River and the New River. They both became conduits when there was a break in a floodgate over on the Colorado River at Yuma, and basically the water came along the Alamo Canal and filled up the Salton Sea as we see it today. The Salton Sea today is about 40 miles long. At the widest point, I'm thinking it's probably 15, 18 miles wide at the bottom of that picture. And it's very shallow. There's a hole up near, probably around where the S is in Salton, that goes down about 40 or 50 feet. But the southern end of the Salton Sea, where the word sea is very shallow. Matter of fact, if you walk out there today, you'll probably not get above your knees for at least a mile or two out into the sea. So it's a very shallow sea. It heats up quite a bit in the summertime, so that the water temperature might approach 90 degrees Fahrenheit at the southern end, especially. And in the wintertime, it actually still stays pretty warm, but just a little bit cooler than that. There's some fish in the Salton Sea. I don't know how much there is these days. There used to be a big fish called a corvina, and then tilapia, as I understand, also used to live in the Salton Sea, and maybe they still do today. There's no natural outlet for the water that goes into the Salton Sea other than evaporation. As I mentioned, there's the Alamo River and the New River are small volume flow rate rivers going to the sea. There's the Whitewater Wash at the north end, and the Whitewater Wash goes through Palm Springs, Palm Desert, La Quinta area. And so heavy rainwater will come down the Whitewater Wash. And so there's a bit of water that comes from that point. But the vast majority of the water sustaining the Salton Sea today is irrigation runoff from the Imperial Valley. That runoff is produced from Colorado River water that comes over in the All-American Canal near the bottom of your picture. And it's gravity fed from Yuma, Arizona, at the Arizona-California border over to near El Centro. And then by gravity, it flows towards the Salton Sea to the north. The Salton Sea to the north is probably, maybe 170, 200 feet lower than where the All-American Canal is. And so gravity makes that water go down towards the sea. Well, that works really well for farmers. They can use gravity rather than pumps to distribute water to the farmland that's out in this area. And those of you who live here know this, and those of you who don't, you can almost watch the vegetables and the hay grow. If you sit down, it grows amazingly fast. And this is all gravity-fed water that goes into the Salton Sea after it's used for irrigating the farmland. Next picture, Mike. So in 1905, after let me back up here just a little bit. So around the turn of the century, some of the first people that were out here that wanted to farm, they wrote a letter to the U.S. Department of Agriculture. I've seen the letter in a book, and they asked for essentially a grant to be able to dig a canal to bring water from Yuma, which is about 60 miles to the east, over to this area to use to grow crops. Well, the U.S. Department of Agriculture wrote a letter back and said, basically, you guys don't know what you're talking about. Nothing will ever grow out there. It's desert. And so the answer is no. Well, they were pretty determined to get water over there, and a canal was dug, which is now basically the Alamo River, I think, for all practical purposes. It was dug by hand with mules and everything but today's modern equipment. They did a pretty good job. They put a series of canals and drains to move the water to where the crops needed to be grown, and it worked great. Well, what happened in 1905 was the head gate where the water was diverted off the Colorado River. And again, this is before Hoover Dam and Lake Mead and Lake Powell and the other infrastructure on the Colorado River. And that head gate broke. And when it broke, the Colorado River, instead of going primarily into the Gulf of California or Sea of Cortez, depending on how you know it, to the south, switched back and flowed into what is now the Salton Sea. And at that time, it was a salt flat, but it filled up with water. That water flowed, as I understand, for almost 2 years unchecked. There's a picture there in the bottom right-hand corner that shows this water coming down across the desert. And it filled up the Salton Sea as we know it pretty much today before they were able to get that water diverted back into the Gulf of California. And then all of a sudden we have the Salton Sea. Now, years ago, a long time ago, when we really weren't out here doing this kind of work, the Salton Sea would periodically delta up going into the Sea of Cortez, and it would flip back into the Salton area, and it would fill up. And the last time it did, it was called Lake Cahuilla. And if you are driving on the western side of the Salton Sea and look towards the mountains, you can see the bathtub ring the last time that it had done that on its own. And that bathtub ring is pretty close to normal sea level out in the ocean. Well, then it dried up. And then again here, when the head gate broke, it started filling up again, but they were able to get it shut off. So at the time, 20 years ago, the level of the Salton Sea was about -220, -225 below sea level. And today it's down to about -240, give or take a few feet. Next slide, Mike. So 1907, the head gates is a picture of them on the right. They got it fixed. The water's now going back into the Gulf of California, but the Salton Sea now is filled up with water. Not a bad thing. It was fresh water. Some of you may have read the history books where around the 1950s, I think everybody thought this was going to be the next Palm Springs, but with a huge lake to play in. Some of the small cities around the Salton Sea were generated. If you go out to Salton City, for example, you'll see paved roads or what's left of them, street lights that were put in place in the 50s. But as the water evaporated, the salt concentration in the Salton Sea increased, and pretty soon folks lost interest in continuing that development, and the developers basically walked away. Now, there's still folks living out there and enjoying it to the extent they can, but it's not what people thought in the 1950s. On the left-hand side, you can see a patchwork of basically it's all crops that are growing, those different colors. The green obviously is crops. The brown is where they've tilled the dirt and it's ready for planting. But there's about 500,000 acres in this area of Brawley, El Centro, that produces crops and hay. And it has brought many a livelihood for the people here in Imperial Valley. Next slide. Along the area of the geothermal field, which is basically in the southern, very southern tip of the Salton Sea. And again, it has no connection to the sea itself because the geothermal reservoir starts about 4,000 feet down approximately. One of the phenomena that occurs here is some of the rock formation down below will produce carbon dioxide when it's heated up, mixed with water, and that carbon dioxide will find a way to the surface. And some of you who've been out here, you'll see mud pots, and the CO2 is really the driver of these mud pots. Some of those mud pots are ambient temperatures, they'll be the same temperature as the air or the ground around them, but some of them are very hot. So if you ever go out to look at them, you want to be extremely careful because it may look dry around that mud pot, but in some cases it could be pretty muddy underneath the crust. And if you fall into it, you probably will need help getting back out. The hot ones are obvious. You'll see steam coming off of them. And the highest that I remember anybody measuring the temperature is about 200 degrees Fahrenheit. So again, you want to be real careful. Well, that CO2 became a valuable commodity in the 1930s. And if you're driving along a road called Davis Road, which is on the east side of the Salton Sea, near the southern portion of the Salton Sea, you'll see remnants of a building that used to be a dry ice manufacturing plant. And there's a picture of the interior machine works that you're looking at right now. This was produced to make dry ice, which is CO2, solid CO2, for moving vegetables to market. You could put the dry ice in a truck, keep the vegetables cool. You could put it in a train car, keep it cool. This facility operated for a handful of years, starting in the late 1930s. And as I understand, there was operation there till late 1940s, maybe as late as 1950. But as modern refrigeration came along, like we see in our refrigerators in our houses, and produced regular water ice, it basically put the dry ice plants out of business. And the way you make dry ice is you bring up carbon dioxide from the ground. And the way they did that is they drilled small wells, about 800, 900,000 feet deep. And the CO2 that was in the formation down there would percolate up through those wells. They would drain off the water, and then the CO2 that was left over, they would pipe it over to this facility. They would run a compressor and compress that gaseous CO2. And then the way you go from gaseous CO2 to a basically ice, dry ice, is you have it in a container and you expand the volume in that container. And that's what you see in front of you right there. They would fill up that chamber with gaseous CO2, and then they had a piston, and they would draw that piston up, and in the snow, the dry ice snow would form right in front of your eyes. You can go on, if you look up Cardex Western Company on the internet, you can find a short video. It only lasts about 3 or 4 minutes, and it actually shows this facility in operation. And then they would take out that ice, that snow, if you will. It looks just like regular snow if you lived up north. And then they would compress it into a block, which is the fellow on the left. He's holding a block now of dry ice. And then that's the dry ice that would go into either a truck or a rail car to keep the vegetables fresh on the way to market. As I mentioned, this shut down around 1950, and lo and behold, another company bought it, and they made it into a hot mineral spa. And you could go out there and take a mud bath or a hot mineral bath. Didn't last real long. It wasn't profitable, as I understand, and it closed down in the 1980s, I think it was. Okay, Mike, next slide. So here we are. You've probably have all heard about the San Andreas Fault. It goes from way up north of San Francisco down to where we are at the Salton Sea. And it's that heavy red line coming from the top of your picture down to about the middle. And if you're familiar at all with the Salton Sea, you can see a small picture right in the middle of the screen that is the Salton Sea. And right where that San Andreas Fault stops, that heavy red line stops, is a small little town called Bombay Beach. And what happens is that San Andreas Fault breaks up into, at least what I refer to as a stair-step type fault. And if you look, you can see a small piece about an inch long, heavy red again. And then if you look over a little bit further to the left, you'll see another red heavy line that's probably an inch and a half long in this picture. And that's the phenomena that has caused the geothermal reservoirs to be there. So up near where that triangle is, that orange triangle, if you took those heavy red lines, you would see smaller heavy red lines if the picture was big enough. And from line to line, where you see those purple kind of heavy lines that are at a diagonal, what happens is as the Pacific plate moves to the north and the North American plate tends to move to the south, it pulls apart those faults that I mentioned that are kind of stair-step type faults. And where the triangle is, there's many of those little faults there that get pulled apart. And that is where the Salton Sea geothermal field resides. And the only way you know that it's there by walking on the surface is you'll see 5 little hills, and they're called buttes. They're old volcanoes. If you look at them today, they look like great big dirt hills, and except for one called Obsidian Butte, and it has a lot of obsidian, which is shiny black magma type rock, all broken up. But that's where we reside. And as I mentioned before, it doesn't have any connection to the Salton Sea itself, as it's much deeper. But it's there, and it is arguably the largest geothermal field in North America, probably the world, that is dominated with liquid salt water. And it's very hot, and I'll show you in just a second why. But it's very, very hot salt water, about 600 to 700 degrees Fahrenheit. It has a tremendous amount of a lot of different types of salt dissolved in it. Sodium chloride, which is table salt, is about 6% of the solids that are in that. Potassium chloride. Potassium is used for a lot of different things, but one of them is it makes potassium-based fertilizers. There's quite a bit of potassium in there. There's a lot of calcium in there. If you've ever lived up in Michigan, calcium as a salt is used for melting snow, and you can buy it in a bag and sprinkle it out on your driveway. Works real good for lowering the freezing point of the snow, which causes it to melt on your driveway. So that's where we're located. And as you can see, we're not too far from the Gulf of California, but far enough so that when the Colorado River was diverted back, it went up to the north to the Salton Sea instead of going into the Gulf of California. And after a couple of years, they got it diverted back down there. So next slide, please. Okay, so the picture on your left, again, you can see where the Salton Sea is inside that blue circle. And the picture on the right is the Grand Canyon. The Colorado River, as you know, goes through the Grand Canyon, and it basically cut the Grand Canyon. And if you've ever wondered where all the Grand Canyon sediment went when it was washed away over millions of years, there's 2 places to consider. One is, as that river water flowed into the Gulf of California, a lot of that sediment went into the Gulf of California. But when it would build up and cause the Colorado to flip back to the north, that sediment went into the Imperial Valley. And I'll show you a picture here in a minute, I believe, that'll show if the Imperial Valley was still connected to the Gulf of California, just how far up it went. But that's where the sediment went. So basically, if you go in the Imperial Valley, you have an upside down picture of the Grand Canyon if you were just to drill a hole and be able to see it. Next slide. Okay, a little bit on geology, and I'm not a geologist, as Mike mentioned. I have a degree in physics from way back, 50 years ago, matter of fact, actually 51 years ago. from Texas A&M. But what happens underneath here, in the picture you see is Red Island, I believe, which is right in the heart of the southern end of the Salton Sea. And so underneath that, you have a phenomena that's described in all these curved, different colored lines or arrows. You have a lot of sediment. As I mentioned, all the sediment that ground up and came from the Colorado River water is there. And over the years, it got packed down. The heat from down below produced that metamorphic rock, which is kind of like hard granite, for example. That magma from down below at times came up to the surface, and it produced these little volcanoes that we have out here. And there is a continuous circulation of heat down below here that provides the heat for producing the rocks that we drill through, but also it more importantly produces the heat for heating up the salt water that sits down in that reservoir, almost a mile down in the ground. And we tap into that reservoir to obtain the brine that actually produces the energy that we use for making renewable electricity. And because of the salts that are in that water that are dissolved, one of which is lithium, we have a process to extract that lithium and then convert it into the compounds that the battery makers want to make batteries. So there's, as I mentioned, there's 5 little volcanoes, and you're looking at one in that picture. And actually, if you go up on that Red Island, which is the name of that one, you'll never know it was a volcano. But when you do go up there, you can get a good panoramic view of the surrounding area. Well, there's 4 more of those. The one furthest to the north is called Mullet Island, and it's on the property that we'll be developing. It's not anywhere near as big as that one. Matter of fact, if you're sitting on Davis Road or an island, you can't even see Mullet Island. It barely sticks up higher than the surrounding vegetation. So the one important thing is this circulation of heat, and the picture that describes sedimentary rock turning into the metamorphic rock to magma to igneous rock and back. That happens extremely fast in this area. As it shows up in the top, it's less than 1 million years. If we were out somewhere else, according to our geologist, that 1 million years might turn into 10 million years or longer. So we have a very fast geological operation going down here, which helps produce our geothermal reservoir. Okay, Mike, next one. Okay, so I'm not going to try to explain this diagram too much, but what I wanted to point out was, if you look over on the left where it says depth, those in kilometers. So the 4-kilometer mark is roughly almost 2.5 miles down. And so 8 kilometers would be 5 miles down. So just to give you a little bit of sense of scale. Well, so over the years, when the Colorado River water would flow back in here, it would bring lots of water, lots of sediment, and the Colorado River water, if you're familiar with it, is hard water. It has a lot of minerals in it, a lot of salts, and deposited that in this area, and then it would flip back to the Sea of Cortez. That deposited brine water, salt water would dry up, but it would leave behind the minerals. And then maybe 800,000 years later, it would flip over again and just kept repeating the process. Well, down below that, what you see in red is basically an illustration showing the magma coming up from down below. And there's a magma chamber 2.5, maybe 3 miles or more down in this picture. Actually, our geologist said it's a little deeper, but it provides the heat source that we enjoy for producing the geothermal reservoir that we work in. Now, this reservoir is probably 15, maybe 18 miles long, and probably about 8 or 10 miles wide as we know it today. And so it's quite large. And the heat coming up from this magma, which is just a little bit closer to the surface here than maybe someplace else in California, provides that extra bit of heat that heats up that salt water that's sitting up above it. And then we can drill into that salt water, and you can actually see what looks like some wells. There's 3 of them. They have a little segmented cone on the very top of the picture with a line going down maybe about an inch. So we just go down into that reservoir of hot brine. We can bring it up in our wells, and in a minute I'll explain how it comes up and then how we handle it and how we put it back down in the reservoir, which is extremely important. Next slide. Okay, so you may have heard the name of our project is Hell's Kitchen. Well, what you see in the picture is in the 1920s, a fellow named Captain Davis built a saloon on Mullet Island. That's the little tiny island, or well, it's not an island anymore, but the little tiny volcano or remnants of it that sits on the land that we have to build our plants. This saloon / restaurant isn't there any longer. Once in a while, we find pictures like this, and we have them around in our office. But in honor of Captain Davis and his saloon, we named our project Hell's Kitchen. And so somewhere around Imperial Valley, I think that sign still exists, and we're trying to find it. We'd like to be able to put it up over our plants as a memento there. Captain Davis and his wife also lived on this little Mullet Island, and it's not very big. You can walk across from one side to the next probably in less than 10 minutes. But he lived there, and in fact, he had, I think, some sea lions out there trying to get him to survive in the Salton Sea, which I don't think that went well. But Captain Davis actually drilled some wells on or near Mullet Island, looking for water, and lo and behold, what he found instead was a lot of hot water and steam coming up. And he didn't have to go down very far to find that, and then a bunch of hot mud. Well, you know, some people took note of that. The oil companies, when they got into California and were looking for different places where they might find oil, came out here and drilled some wells, thinking that there should be oil down here, according to all their scientists in the day. And this is probably in the 1950s, early 1960s. Well, they didn't find any oil either. And in fact, what they found was a lot of very hot water, which they weren't interested in. So they packed up and went away. But a little bit later on, around the 1980s, when renewable energy was beginning to gain some favor because of the energy crisis in the early 1970s, some folks decided, hey, if they could tap into that hot water, they could take advantage of the energy that's in there, maybe produce some steam, turn a turbine, connect it to a generator, and make electricity. And they did. There was one fellow by the name of Mac McCabe, who was one of the early pioneers. In the 60s, he was up at the geysers in Northern California, just north of San Francisco. And there's a big geothermal field up there, but it doesn't have liquid water. Instead, what it has is about 10,000 feet down, it has a gigantic piece of granite rock, miles long, and it's sitting at about 600 degrees or more. And it was basically boiling the water in the 10,000 feet above it, creating steam. Well, McCabe decided he could take that steam and use it to make electricity. So he drilled some wells, built some plants, got it started. Pretty soon, Unocal drilled more wells, built more plants, Pacific Gas and Electric, put some power plants in, and lo and behold, the geysers geothermal field was born. And they still exist today. They make electricity, goes into PG&E's system as renewable energy. Well, down here, McCabe then came down here in around 1980, started poking around up near the Salton Sea again, and obtained some money, drilled some wells, found that, hey, this is liquid brine, liquid salt water, very hot, and he could take the steam out of this water by basically just pushing the water through a wide spot in a pipeline into a vessel, and the steam would come out all by itself. He could put the steam through a turbine, make renewable electricity. And that became Magma Power. Magma Power then, over the years, became a partner with Dow Chemical, and that's how I got out here. Dow was very interested in the 70s and the 60s with renewable power, and especially in the early 70s during the energy crisis. A fellow named Levi Leathers from Texas got to know McCabe and said, hey, here, we Dow can help you a little bit, design your plants. We don't want to take any money, but we'll take stock in your company. And over the years, by around 1990, 1992, Dow owned almost half of Magma Power. And since the late 80s, they were loaning people to come out and help McCabe design, build, construct, operate these plants. And that's how I got out here. In 1992, after I had been at Dow for just about 20 years, I had the offer to come out and develop engineering technology for Magma Power, and I came out in 1993. Well, Magma was not the only one out there. Union Oil Company, Unocal, right next to where Magma is, did the same thing. They built some geothermal power plants, much for the same reason. Actually had 3 of them running, 2 small ones and 1 fairly good sized one. And in 1992, Magma bought Unocal's geothermal operation, both here at the Salton Sea and abroad in Philippines, Indonesia. And so when I came out here and I was asked to develop engineering technology now for Magma Power, which also included Unocal. And I stayed. I cut my string with Dow. I love the hot weather and stayed here. And pretty soon, Magma Power became Berkshire Hathaway in the late 1990s. And during that growth period, they ended up with 11 power plants. And we built actually 1 zinc extraction plant. We extracted zinc from the brine and made what's called special high-grade zinc ingots. This is 99.995% pure zinc, and we sold it under contract. That plant only lasted about 5, 6, 7 years, and then it was taken down. And at the time, I was already gone off to do other things. Next slide, please. Okay, so here we are today, many years later, and the Berkshire operation still operating, has 11 plants. They plan on building some more. In 2010, a small company called Energy Source built a plant called Hudson Ranch, actually a mile down the road from where we're going to build our first plant. And I was a part of Energy Source when they built that. Uses the same technology that McCabe and Unocal developed back in the early 80s. And that technology was designed to manage the silica that was dissolved in that hot brine. Silica is sand. And if you put it in water and you heat it up high enough, it'll dissolve, just like if you put salt from your salt shaker into a glass of hot water. Well, you have to be a little bit hotter to dissolve the silica. But if you pull up the geothermal brine that's deep in the ground, it's saturated with silica that's already dissolved. What happens as you take energy out of that brine to produce electricity, the silica will start to crystallize out as sand as we see it. And if you look at it, it'll look like dirty sand because it has a little bit of iron that came with it. And it'll look just like the beach sand if you go over on the Pacific Ocean. And so to control that silica, Unocal and Magma designed a process called crystallizer reactor clarifier, just to give it a name. And to keep the silica from crystallizing on the pipelines and the equipment and plugging up the pipelines in the equipment, they put together a process that would make that silica crystallize in certain areas, but not on the walls of the equipment. And then it would go to what's called a clarifier. And a clarifier is a great big round tank that has it's a rake that goes around and around like a paddle slowly in that clarifier. And the silica, when it forms the crystals, as we know, sand, would slowly drop to the bottom. And then when it does, you could actually remove that silica, even though the tank's full of water, by running a pump at the bottom, and it would slowly pull the silica off. Well, it took a few years to get that design down well, but once they did, all the power plants out here use that same technology. It runs very good. We know how to run it very well, and it keeps the silica concentration down low enough so that it doesn't plug up the power plant. So controlled thermal resources came along about 2011, 2012. Rod Caldwell, our CEO, is from Brisbane, Australia. And if you talk to him, you'll know he's from Australia because he has a bit of an accent. But he grew up out in the outback, and he has, quite a career. Played rugby over there, did a lot of farming on his family's farm, and then eventually got into commercial real estate and did very well. Built a lot of big warehouse type things like Walmarts around Australia, but finally got tired of that kind of business, and he wanted to do something that was green. And so he looked at solar to produce electricity. Didn't excite him that much being in Australia. And then he got turned on to geothermal energy and caught the bug. Met a fellow that had some geothermal background over there, and they started looking around the world for where there was a geothermal reservoir and a market for that green renewable energy. Well, it didn't take him long to get to California in the United States. And then once he was in California, it took him even less time to realize that the big geothermal field is down here in Imperial Valley at the southern end of the Salton Sea. So he showed up out here. I didn't know him yet, and started doing some work to secure a portion of the Salton Sea geothermal resource so he could build a geothermal power plant. Lithium wasn't even on the horizon at that point. And finally, he secured a lease from the Imperial Irrigation District, who happened to own the subsurface mineral rights underneath what you see here, plus quite a bit more to the left off your screen, and secured a lease that took him probably a good 2 years to negotiate. And finally, in 2016, the lease was executed, and now Controlled Thermal Resources had a lease on the surface and the subsurface for about 9 square miles. And what you see in front of you comprises maybe 3 square miles, roughly. And then the next thing to do was to hire some consulting companies to actually do some studies to estimate about how much electricity we might be able to generate by pulling brine out of the area that he just leased. And the number came back to about 1,100 megawatts of electricity. That's about half of a nuclear power plant. Diablo Canyon in California produces around 2,200 megawatts. Well, okay, so here's half. So that looked promising. And I met Rod, in 2015. I was using an office in an engineering facility down in El Centro, working with the folks that were there. And Rod, as it turned out, ended up renting an office in the same building we met. And the rest is history. We've known each other since then, have become good friends and good business partners here. And we started developing the first geothermal power plant of controlled thermal resources. And so the way you do that is, okay, first of all, you find the reservoir, which Rod had already secured. And then you have to learn a little bit about what's down in the subsurface so you know where to drill the wells. And to do that, you have to use what's known as some seismic work, where you actually generate a vibration on the surface. And you may have seen these. Some of these are called thumper trucks, and the truck will stop on, somewhere on the land, and it has a big flat plate underneath of it, and it'll thump the ground. Well, if you do that and you have instruments called seismometers set up in array, just like oil and gas, you can get a pretty good picture of what the subsurface looks like. In this particular area, it's highly fractured. As I mentioned, the San Andreas Fault comes down to Bombay Beach, which is probably 8 miles to the north of here as a crow flies. And so all this area is where these stair-step faults are, and it has a lot of fractures in the formation down there. And so you use those fractures to target where you want to drill a well. These wells are about 8,000 feet deep, roughly. And the reservoir starts about 4,000 feet down. So you have about 4,000 feet below that of a well that can take brine, bring it up to the surface. And if you put it through a big wide spot in the line, like a vessel, and run the vessel, say, half full, steam will disengage. That's the energy portion. And you can take that steam, clean it up a little bit by squirting water in it in a spray type fashion. And then that steam can go through a turbine, turn it, and make electricity. And then you take the steam, you condense it back into liquid water, put it back in the brine, and put it back in the reservoir. The reason we want to put it back in the reservoir is because if you just take the hot water out and don't put it back in, at some point in time, that water table down there will start to drop. And in the way to keep a geothermal reservoir healthy is to maintain pressure. And the way you maintain pressure is you put about as much back in the ground as you took out. And now what goes back in the ground is a little bit cooler. So if you have a tea kettle on the stove and you have the top closed so that you don't get any steam out, you don't get any whistle, and you turn on the burner, you know that the water inside that tea kettle gets above the boiling point of the water. That's how you produce the steam if you open the valve. Well, that's exactly what we do here. And if you open the valve and let the steam out, the water cools back to what's called its atmospheric boiling point. So that's when you get no steam, but the water is right on the cusp of boiling. Same thing happens here. We take out enough steam so that the brine goes down to its boiling point. So if the brine, when we bring it up from the well, let's say it's 500 degrees Fahrenheit, and we take all the steam that it will produce out of it and use it to make electricity or use it for something else, the liquid cools down to its atmospheric boiling point. Well, the boiling point of this salt water is about 225 degrees Fahrenheit. So it's a little bit higher than just regular clean water. If you were at sea level, clean water would boil at 212 degrees Fahrenheit. Well, our water will boil at about 225 degrees, give or take a few degrees. So these power plants are real simple. We take steam out, we take the resultant brine, and as I mentioned, we have to manage that silica. So we remove the silica as a crystal, and then the water that's left over after we take the steam out and we've removed the silica, we put it back into a well, back into the reservoir. Now, we don't want to put that water back in real near where we just took it out, because this water is a little bit cooler. So we have a rule of thumb where we'll put an injection well about the bottom part of the injection well, where the water is actually going into the formation, about a half a mile away from where we took the water out, at least. And so we could have a well going off in one direction to bring brine up, and we could have a well going off in an opposite direction to put the brine back in. The other thing that we typically do out here is we'll inject the water back into the reservoir a little bit deeper than where we take the water out. And that's just to help Mother Nature heat that water back up. We'll see it again way off in the future, and we can repeat the process. So that's the renewable side of that. And it's the heat from down below that's heating that back up. The time it takes that water to get from that injection well back to that production well, I can tell you, is probably much more than 40 years, because we've been operating plants out here since 1982, and we don't see that same brine coming back. And the way we know that is we measure the chemistry of the brine. Brine has about half of the periodic table of the elements in it, if you remember your high school chemistry. And so we measure the chemical makeup of the brine to see if we're seeing brine that came back that looks like the brine that we put in as we injected the brine back into the reservoir. We watch temperature, we watch pressure, and by monitoring those things, we can tell if we get any short circuits from an injection well to a production well. So that's the power plant. Now, I mentioned that there's a lot of different elements in this brine, different salts in this brine. Sodium chloride, as I mentioned, is table salt. Potassium chloride, if you took it out, you can convert it into fertilizers. Well, one of the salts in this brine is lithium. And lithium exists down there as a salt, lithium chloride. It looks just like table salt. If you had a bottle of it that was already crystallized and dried, you probably couldn't tell the difference between that and table salt. Might taste a little bit different, but you wouldn't be able to see any difference by looking at it. Well, the lithium chloride is dissolved in the brine. There's still lithium chloride in the rock, but the time it takes to go from rock to being dissolved in the brine is probably thousands of years. But the amount that's in the brine is about 200, a little over 200 parts per million. So for every million gallons of salt water down there, brine, you have about 200 gallons of lithium chloride down there. So we call that parts per million. So for every million parts of water, we have 1 part of lithium in this case. And so when the scientists and the engineers do the calculations of how much lithium is below there in the area that we have control of for developing, we estimate that we can produce, when everything is fully developed, about 300,000 metric tons a year of lithium hydroxide. And lithium hydroxide is one of those compounds that the battery makers want to use for making batteries for electric vehicles. And so that's a lot. And so we want to produce that material for sale. So because we bring the brine up anyhow, if we have a technique to reach in and extract that lithium, then that will enable us to then to convert the lithium into the desired compound and sell it. So if you look at this diagram on the lower right, you'll see a long skinny plant right along looks like a green roadway area. And that's an illustration of what our first plant will look like. That makes almost 50 megawatts of electricity, and it makes about 20 to 25,000 metric tons of lithium hydroxide. And then at the very bottom end, it has a water pond, which we actually probably won't have a water pond there. We'll use a tank. Instead, we need water in our process. So that's what we call our stage 1. Stage 2 will look just like stage 1. It might be shaped a little bit differently in terms of how we lay it out. And if you look up kind of in the middle of this diagram, you'll see some rectangles with illustrations of buildings on them that kind of look identical. There's 1, 2, 3, 4, 5, 6 of them up there. And again, this is an illustration. Those would be the future plants that make both power and lithium. We plan to produce the electricity. We'll use the electricity to run the lithium plant. And we've designed basically an integrated system here where some of the steam that we take out of the brine, the energy that we take out of the brine, instead of using it to make electricity, we'll use it as a heat source in the lithium process. So the lithium process requires in places to evaporate water. And usually to evaporate water, you need heat generally. And so we'll use the renewable steam as our heat source. So we have virtually no fossil fuels in these plants. This is truly green lithium. And when these plants are built, this will be the only place in the world where lithium will be produced completely 100% with renewable energy. So we just call it green lithium. And the automakers are very, very interested in this because the carbon footprint is essentially or practically zero. The battery makers for the same reason. And we're just really excited that we've been able to design this plant where we can use the renewable electricity that we produce and the renewable steam that we have to actually make our lithium. And once there's enough electric vehicles out here, we won't even have gas-fired vehicles for our maintenance and our operating work. People will have electric vehicles. The big buildings that you see, and I can see 1, 2, 3, 4 of them, they're just an illustration of potential battery maker co-locating next to our lithium plants. We're talking to all the battery makers in the world. They're all excited about the possibility of building a plant right next to our lithium plant. And the reason is, if we do that, then we can, via a pipeline, move the lithium product over to the battery maker, and we don't have to ship it anywhere. And then the battery maker can make his batteries, or at least the front part of the batteries, right here. If he does, then he would buy renewable electricity from us, and he would buy renewable steam from us. And now his battery is using green lithium, but his battery is essentially green as well. So there's a big push to be able to do that. And as I mentioned, the battery makers are all talking with us about this possibility. We'll see if it comes to fruition, but it would be a huge boon to Imperial Valley and to California. I was going to mention one more thing here, and actually I'll get to it a little bit later. And I was going to talk a little bit about jobs, but I think that's a slide coming up. So again, this is the first part of our overall development, and what you see here would produce about 370 megawatts of electricity and about 180,000 tons of lithium product. Now, as you probably know, the Salton Sea shoreline is receding, and that's primarily a result of water transfers and evaporation in the Salton Sea. It is projected to reach a sustainable level around 2028, 2029, as I recall. And as it recedes, the shoreline recedes, it actually allows us to build out here. Well, there's a negative aspect of the shoreline receding, and it exposes playa. And those of you who live out here know that when the wind blows hard, it picks up dust in the desert. And so we want to minimize dust from here. Wherever we have our footprint, such as this, and we don't really show it here this way, but we'll take care of the dust problem in our area by basically covering the dust. It might be with rock or buildings or whatever, but we'll cover the dust. We expect that just producing electricity and lithium in the area that we have, we'll probably have 1,000 workers out here. And so we have a big employment group that we want to protect the health from as well. If the battery makers co-locate here, they have far more workers. There's probably 3,000 to 4,000 workers as a result of the battery companies locating right next to us. So we want to minimize any dust from our area, and that's in our plan. Our footprint is small, so in between where we are, there's plenty of area for others to develop, whether it's a solar field or some other type of facility. And our goal is to basically cover the playa that's being exposed in our location. Okay, next page. Okay, so quickly, just I'll give you a little bit of how the process works. I mentioned that we bring up brine from deep in the ground. We separate steam from the brine. The steam goes into a turbine. The turbine's connected to a generator, spins the turbine. Just like you see in a jet airplane, it's spinning and makes electricity. The brine, if it were just making electricity, it would go right back in the ground at that point. Instead, what we're going to do is it'll go over to the next block. We'll actually reach in, extract the lithium, and then we'll put the brine back into the geothermal reservoir. And then we have to convert that brine because it's in the form of a salt, liquid lithium chloride. We'll produce either lithium hydroxide or lithium carbonate, depending on what the battery maker specifies. In our first plant, we're going to make lithium hydroxide. And in the world out there of batteries, they're about 50-50. About half of them want a carbonate compound, the other half want a hydroxide compound. And then there's batteries. It goes off to the GMs of the world, the Stellantises, Fords, and they make electric vehicles. We have a completely enclosed system. This brine is always inside pipes in vessels. We have virtually zero emissions, except for a little bit of carbon dioxide that comes up with the brine. We have no solid waste discharge from our plants, and we have no water discharge from our plants. So we try to reuse every gallon of water as many times as possible before it goes back into the reservoir. We have a study working specifically on that for our first process. We're not an open pit mine, so we have no tailings. If you're familiar with lithium production down in South America, it's similar to that very first picture I showed you where they have an evaporation pond and they evaporate water, leaving the salt behind. We don't have that. We have extremely small footprint. And last but not least, we're green. So next slide, Mike. Okay, so that's Rod Caldwell right in the middle picture. With Cesar Flores, one of our laboratory people. The picture on the left is when we were drilling one of the wells. That's a drill rig. It looks just like an oil well drill rig, which it is, but it has a little bit different equipment on it. The picture on the right top where it says lithium supply agreements, we have an optimization plant out there right now. It's very, very, very small scale. And we're flowing brine out of one well and injecting it into the other. We have 2 wells out there that we've drilled so far. And we're taking a very small side stream off that, and we're doing some optimization work on relative to how to improve the economics on the lithium extraction itself. And we're just about to shut that optimization plant down for some maintenance. We may start it back up in a month or so, but it's about to come down. It's been running about 6 months. We've obtained a lot of information on how to optimize certain portions of our plant, and that information has been transferred over to our engineering company that's doing the engineering. We recently signed a memorandum of understanding with Fuji Electric. Fuji Electric in Japan is the supplier of the turbine generator system. So our first one is almost built. It'll be ready to ship over here later this year. But we just signed a memorandum of understanding with Fuji for a handful of additional turbine generators for the future plants that we have on the docket. Just a few weeks ago, Governor Newsom was here, and that's a picture of him at the site. I wasn't here that day. I was out of state, but Rod Caldwell was there with him, and Newsom toured our facility and had a good time. So next stage, please, our next slide. Okay, so the brine, as I mentioned, has a lot of material in it. So everything that you see in red, or a red circle around the element, is contained in a brine. Some of it is in large concentrations, some of it is in extremely small concentrations. But we have a lot of material so that in the future, if we want to extract manganese, which is also used in electric vehicle batteries, we have a fair amount of manganese, and we'll develop a process to do that. There's a little bit of silver and even a smaller amount of gold in this brine, not really enough to make it worthwhile to take out, but it's there. And you can see the rest that we've highlighted just for example. Okay, next slide, please, Mike. All right, so there's the same picture we saw before. We've just termed it, it's a clean energy campus. Everything out there is run with clean energy, renewable energy, green, or steam. And we plan to have the entire development basically be a green development. And you can see some of the names for stages. Again, this is an illustration. I don't think it'll be quite this close together, but it'll give you an idea of how it may turn out. Next slide. Oh, that's it. So any questions that you have?
Yeah, let me go back here, and I will stop my. I'm going to stop my screen share, and so we should be back. We are back here. I believe we're back now. Okay, so we have had some questions come in, and I've looked ahead a little bit here as we were talking to at least give me a bit of a start. And let me see, and then I'll go back again and take a look. And there's a couple of themes, I guess, that we had in some of our questions. So one of them was, I guess, around the idea that right now lithium is at the very center of what we want to call like our electric future, whatever you want to call it. I mean, lithium is in high demand, but technologies change. This is a considerable investment, and already, there's sodium-ion batteries, different things being made. So what do you see for the future? I mean, because this is a considerable investment, you've got to be looking out, I don't know, 20, 30 years at least. What do you think? Do you see a really secure place for lithium, or do you think that's going to change?
No, actually, I see a real secure place. Lithium is the lightest element, and it happens to have a lot of charge capability. And so electric vehicle batteries in particular, weight is extremely important. So they want to make the lightest weight batteries they can. Sodium is a bit heavier than lithium. It's not that it doesn't work making make a great battery. Lead makes a great battery. We're all probably used to that in our cars,
Yeah.
And so for mobility, weight is extremely important. So lithium, I think, is going to be extremely tough to beat. It is the lightest metal, and it happens to have good charge. Sodium may work pretty good for maybe a heavy truck, perhaps. Definitely stationary batteries, and you probably have mostly seen, all have seen the stationary batteries that the power companies are starting to install. So there's a place for all of it, but I think lithium is going to be around for a very long time.
Okay. Okay, so we have a couple of questions here in different ways. They ask about water. Now, you mentioned, of course, water, you know the situation for water here in the Southwest and what that is. And so people make comments like they've heard or they want to know how much water is needed, like in this refinement process, I guess you could call it, and what the source for that water would be.
Well, clean water in the Imperial Valley ultimately comes from the Colorado River. There is some pockets of fairly clean water. Ocotillo down Interstate 8 obviously has some clean water. There's some pockets out there, but the vast amount of water comes from the Colorado River. So again, that's one of the drivers for our study to how many times we can reuse a gallon of water and not just use it once and throw it away. So water's precious. We really appreciate how precious it is. And so we've tried to design our process to use the least amount of water. But when you make these kind of compounds, whether it's lithium or sodium or any other compound, it does use a bit of water. And so we established a study right from the get-go that once we had our process designed, that we would go back and look at how we can improve it for minimizing the use of water.
Okay. So you think, though, with the water, with the way the Imperial Valley is set up now, that there's access to the water that you need?
We do. We have access through the Imperial Irrigation District. For years, they've had a small set aside for industrial use. Actually, they have a small set aside for city water, for the cities. and we'll actually utilize the industrial water set aside. We have a request into the Imperial Irrigation District already, and that'll be our primary source of water. As I mentioned, when you take steam and you condense it, it condenses back into water. That water is good water. It's very clean. We'll use that water in our process. Again, it's to minimize the take of fresh water, but we will end up using fresh water too.
Okay. All right. So as part of this process, you're going to generate a lot of electricity. Is that electricity that's going to be used on site, or is that electricity going to be, sold out to the grid? And, right now, like San Diego County is looking at a power management plan, they're looking just within the county, but, trying to decide where future power will come from. So is this going to be power that's going to be out there and sold for homes and things, or do you think you'll be using it all?
It'll be both, Mike. Out of the first power plant, which will make just under 50 megawatts to be used, 40 of that will go to the Imperial Irrigation District. So presumably then they'll turn it around. It'll go to residential use in Imperial Valley and up in the Palm Desert, La Quinta area. The other 10 megawatts, or just under 10, we'll use for the first lithium plant. So at the end of the day, we'll probably use maybe 40%, give or take, of our power that we generate internal for mineral extraction and production, and the remainder will be available for sale elsewhere, whether it's Imperial Irrigation District, Southern Cal Edison, San Diego, basically whoever wants to negotiate some power sales with us.
Yeah. Okay. So let's see. So I have a comment in here. I was just looking at it and I just sort of lost it. Was a person who, let me see here, who is a teacher, I think. And let me find that. I kind of lost it here. So this person says, I grew up in the Imperial Valley and I'm an engineering professor. If I wanted to connect with CTE, possibly to get some brine for analysis and working with my students and class and things like that, would that be possible? And who would I contact?
It probably would be possible. And I would suggest at this point, just give them my cell phone number and my email. And
okay. Okay. So I don't have the name of that person. So if you, you can contact me, then I'll get that to you. Let's see. This is a question here from Bill, and he says the silica sand is considered a hazardous material and is being buried off of Highway 86 presently. With increased production from the wells, how will the silica sand be dealt with?
Well, first of all, the silica that's out there off of Highway 86 comes from the Berkshire Hathaway operation. And it's normally non-hazardous, and it's every truckload is tested by Berkshire. I mean, I used to run that organization, but we all do the same thing if we're running that. It is tested. It's non-hazardous normally. Not that it can't become hazardous if their process was out of control and they precipitated another element out of the brine, then it's possible that it could become a hazardous waste, and it would not go out to that particular landfill. It would have to go to a landfill that was permitted for that type of hazardous waste, which is not in the Imperial Valley. It's not even in California. It would end up going somewhere else if that were to be the case. In our case, we don't plan to have any waste that goes off site. Instead, our silica, it'll be one of our products. We'll sell it.
Okay.
And in fact, we have a buyer already for the product. It makes great cement. And this one company wants to make a CO2 free cement. I'm not sure exactly how his formulation works, but he wants to purchase the silica that we'll produce.
Okay. And I have another question. It's kind of, I guess it's kind of the same thing, but you could just say if it is, if you feel like you've answered it. But this is from Rob and Lori, and they say, where does the silica SiO2 go? Does it get in, some of it get injected back in solution with the steam, or is it all remain on the surface? It sounds like it all remains on the surface. Is that right?
It does. So once it precipitates out as a solid, it does not go back in. So in the case of Berkshire, it goes to a landfill. In our case, it's sold as a product.
Okay. Let's see. I guess it's a comment here from Susanna, and she says, we got to tour a geothermal plant with ABDNHA, which is our organization, a year or so ago, and it's impressive how clean the lithium production is when it's combined with geothermal. And she just goes on to say the thing people need to understand is they think that this has something to do with draining the Salton Sea, and that she thinks it needs to be emphasized. This has nothing to do with that. This is well below the Salton Sea.
Yeah, excellent point. There's absolutely no connection. We just happen to be physically located next to the Salton Sea.
Okay, I have a question here from Teresa, and she says, what time frame is estimated for this to be fully operational?
Well, our first one will actually complete the power portion of the project first, and that's by design. And our target is the end of 2024 for that first power plant. And we're working hard to maintain that target. And then the lithium plant, again, by design, we want to have it not ready to start up until after the power plant is up and stable and in commercial operation. And in our case, the first lithium plant is in the latter part of 2025. Takes a bit longer to build, a bit longer to go through the startup sequence on the lithium plant.
Okay, so we have a question here from Sanjeev, and it looks like a pretty technical question to me. It says, how do we separate the lithium fluoride from the dozens of other dissolved salts?
Okay, so first of all, it's not lithium fluoride, it's lithium chloride. Looks like table salt. And we're using an adsorbent process where as the brine goes across this adsorbent, the lithium tends to adhere to the surface of that sorbent by design. It has high selectivity for lithium, low selectivity for the other materials that are in the brine. And then we stop the flow of the brine over that sorbent material, and we flow water over it, and it takes the lithium off. And now we have lithium in water. So that's fundamentally how that works. These are relatively small columns. They look like a piece of pipe with this sorbent material inside, and we'll just have many of those to get the capacity that we want to have for the plant.
Okay. Comment here from Gabrielle. It says, do you envision basically that is there anywhere else in the U.S. that can produce the same amount of lithium, or basically, I guess, how does this process here measure up against your competitors, I guess, at least in North America?
Actually, there's 3 developers on the Salton Sea geothermal reservoir: Berkshire Hathaway Energy, that's one. Energy Source Minerals is the second one down the street, and us. All the lithium that we produce, all 3 companies, I'm sure will be sold right here in the U.S. And we won't even be competing against each other because it's going to be highly sought after. It's produced here in the U.S. It's made into the final product here in the U.S. And well, that's what it is. So I think it's all going to be right here. So I think that the lithium out of the Salton Sea geothermal reservoir will be the most highly sought after, ahead of spodumene, which is out of an open pit mine from Australia, or the lithium that comes out of South America in the big evaporation ponds. In the United States, there's some other lithium developments going on, and hopefully they'll all do good. The United States is not forecast as being a big producer of lithium, but the Salton Sea geothermal reservoir, once it really starts to get developed, probably will be the single largest lithium developer, at least in North America, if not worldwide.
Okay. All right, I have a comment here, and I think it's probably making a comparison somehow to fracking. And they're mentioning and asking about earthquake risk and splitting pipes and fracking has been pointed to as a cause of earthquakes, and with this already being right there on the San Andreas Fault, what can you make any kind of comment about that? Would it impact that at all?
So first of all, we don't frack. If you were to be able to look at the formation down underneath, it's already highly fractured to the point where it would be very difficult to fracture it more if you even wanted to. But because it's already highly fractured just by Mother Nature, we don't have to fracture. And when we inject the brine back into the ground, that's how the fracking operations go that you hear about. We don't have very much pressure putting the brine back in the ground. And in fact, a lot of times we don't have to add any pressure at all. It's the weight of that column of brine going back down is enough to push it back into the geothermal reservoir. So we don't frack. We're already highly fractured, so we don't have to do that. And we don't use pressures that are anywhere near the fracking pressure if our formation wasn't already fractured.
Okay. And so with that kind of wraps it up. I mean, I just looked over our comments and questions, and there's quite a few people in there who just said, thank you. It was a great presentation. They learned a lot. They look forward to learning more. And people asking maybe someday when you get things rolling there and you're set up for people to come out and see this operation in person, maybe we can do some tours or something like that over there.
We'd love it. We'd love it.
Okay. And so with that, I want to thank you, Jim, for putting this together and doing this. It's been a lot of good information for us. And I'll say goodbye to everybody for our webinar tonight.
Well, thank you, everybody. I appreciate your patience and listening to me a little bit long-winded, but talk.
Thank you very much. Okay.
You're welcome.
Good night.